Hello everyone, welcome back to the channel. Today we are going to discuss about the most famous molecule in organic chemistry, which is benzene. Benzene was a complete mystery for a long period of time. Then a chemist named August Kekulé said that benzene is actually cyclohexa 135 triene. 135 triene. So it is actually cyclohexa 135 triene. Okay, so that means this is the structure he proposed. So we have double bond as position 1, position 3, and position 5, carbon number 5, right? This is what was proposed by August Kekulé. He said that the structure actually looks like this, alternating single bonds and double bonds. But there is a massive problem. If Kekulé was right, benzene should exactly behave like an alkene, right? Because we know that alkenes have carbon-carbon double bond, and we have 3 double bonds here. So benzene should actually behave like an alkene. It should give addition reactions, right? Decolorization reaction with bromine, but it does not happen. Today, we're going to look at the modern structure of benzene and 4 undeniable evidence that shows us that in fact Kekulé was wrong. Let's get started. Now let's forget about Kekulé's alternating double bond structure of benzene and look at the modern structure of benzene. We know that electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. In an exciting state, the electron from the 2s2, one of the electron from 2s2 jumps and goes into the orbital, suborbital 2pz1, like this, 2pz1. So now we have here 4 unpaired orbitals. One is the s, the other is 3p, right? So these orbitals can overlap and they can create sp hybridization, sp2 hybridization and sp3 hybridization depending on compounds. Now let's look at what happens in benzene. In benzene, we have the sp2 hybridization. That means one s orbital overlapped with 2p orbitals and produces sp2 hybridization. One of the p orbital is unhybridized. That is very important here. So out of these 3 sp2 hybridized orbitals, one of them overlaps with the 1s orbital of hydrogen and produces a sigma bond. Another sp2 hybridized orbital overlaps with another sp2 hybridized orbitals from this carbon, the other 2 carbons, and produces sigma bond here. The same thing happens with these 2 carbons here too. So these 3 sp2 hybrid orbitals are overlapping with the other orbitals of 2 carbons and 1 hydrogen and producing 3 sigma bonds. But we know that there are 4 electrons in the outer shell of a carbon, right? So where is the 4th electron? The 4th electron is here. The 4th electron is in the unhybridized p orbital. Now the unhybridized p orbital is actually perpendicular to the hexagonal carbon system, perpendicular. So there is some part up and some part down, right? Hexagonal carbon systems, top part and bottom part, it looks different in the 2D structure, but it's actually perpendicular to the surface, the carbon system. Okay, now in the benzene ring, the carbons are closer together. So these orbitals, these unhybridized p orbitals can overlap side by side and create a pi system like this. The top part overlapped with the top part, and that gives us a pi system like this. Now remember that this overlapping doesn't just happen in pair, it happens across the whole ring. So we have a pi system like that. Remember, this is on the top side of the hexagonal carbon structure, right? It's on the top of the hexagonal carbon structure. We also have another carbon system, another pi electron system at the bottom, like this. So in the whole structure, we have 1 carbon making 3 sigma bonds with 1 hydrogen and 2 other carbons, and the unhybridized p orbital is creating a pi ring upside and the bottom side of the carbon system. That gives us electrons, they are moving around the whole ring. We call them the delocalized pi system, and this because of this delocalized pi system, electrons are not stacking up anywhere and it's not producing localized pi system like in alkenes. And as the electrons are spread out, and because of the dilution of the electron density, benzene is very stable. Now we are going to look at evidences that actually proves this thing and proves that Kekulé structure is wrong. Let's see them. If we add hydrogen in a standard carbon-carbon double bond, energy will be released and the enthalpy change will be minus 120 kilojoule per mole. If Kekulé's structure is correct, we have three different double bonds in the benzene structure, and the energy change, the enthalpy change here will be 3 times of this one, right? As we are adding benzene hydrogen in 3 different places. So it comes as 360 kilojoule per mole. But when we put real benzene through the hydrogenation process, the enthalpy change comes as at only 200 minus 208 kilojoule per mole. Now this is a massive 150 kilojoule per mole less than Kekulé's proposed structure, right? What should have been. This shows that benzene is much lower in energy and benzene is much more stable. It directly disproves Kekulé's structure of benzene. Now let's look at the geometrical and mathematical side. We know that a standard carbon-carbon single bond has a bond length of 0.154 nanometer. And a carbon-carbon double bond has a bond length of 0.134 nanometer, right? So the lengths are not identical, they are different. According to Kekulé's structure, if we have double bond and single bond in there, just like this one, this hexagon should not be even. This hexagon should be a distorted hexagon, right? Because the bond lengths are different, so it will look completely distorted. But when we pass real benzene through X-ray diffraction, we see that the hexagon is even and all the bonds are identical. All the carbon-carbon bonds in a benzene are identical. They have a bond length of exactly 0.140 nanometer. And that's why they have a nice bond angle, accurate bond angle of 120 degree. So it also shows that these things are not matching. The benzene is even. The structure of benzene that we can see in X-ray diffraction is very even. They have a same bond length for each of the carbon-carbon bonds, and their bond length is also nice 120 degree. So mathematically and geometrically, Kekulé's structure again is wrong. We know that alkenes rapidly decolorize bromine water solution, right? For example, if we have ethene and ethene reacts with bromine water, bromine solution, we are going to get dibromoethane, right? Dibromoethane. Okay, now how does this reaction actually happen? Let's understand the mechanism here. Now, in a standard carbon-carbon double bond, we have pi electrons which are localized. So these pi electrons create a strong area of negative charge. When a bromine closes in, these electrons, the strong area of negative charge actually repels the electrons in the bromine away. As a result, we have a delta plus bromine. That means the bromine has been polarized. Now this delta plus bromine will attack the double bond and a reaction will happen. As a result, we are going to get that dibromoethane. As in the product, the bromine is not existing anymore. The orange color of bromine is gone and the solution becomes decolorized. But benzene does not give this decolorization reaction. Now, why is that? Because in benzene, in real benzene, the pi electrons are not localized, they're delocalized. They're spread evenly throughout the ring. As a result, the electron density is diluted, and because of that diluted electron density, it cannot successfully polarize the bromine. So bromine cannot actually attack and react. That's why the decolorization reaction never happens. If you actually want to decolorize the bromine water using benzene, you need a halogen carrier as a catalyst. For example, ferric bromide, aluminum bromide. So that's a different thing. You can talk about it in another video. So for now, because of the diluted electron density inside the benzene ring, as the electrons are spread out evenly or throughout that ring, it does not have the ability to polarize the bromine, incoming bromine. That is why benzene does not give the bromine water test, which again disapproves the structure of Keku. Now finally, let's talk about the chemical fingerprint, IR or infrared spectroscopy. A normal carbon-carbon double bond shows characteristics absorption peak at around 1650 centimeter inverse 1. So if we have a normal carbon-carbon double bond in a compound, we are going to find a peak 1650 centimeter inverse 1, right? But when we put benzene through a IR spectrometer, we actually find peaks at 1450, 1500, and 1580 centimeter inverse 1, which are the characteristic peaks of double bond or delocalized bonds. So again, the main normal carbon-carbon double bond peak is missing. So our benzene cannot have a normal carbon-carbon or standard carbon-carbon double bond. We have delocalized electrons moving around. That is why we're finding these peaks as 1450, 1500, and 1580, right? So this again disapproves Kekul's structure, and it shows that benzene cannot contain localized pi bonds. So where are we standing now? The identical bond lengths, the unexpected hydrogenation energy, the IR spectrum, and the resistance to addition reaction all point out to one thing and one thing only. Benzene has a perfectly symmetrical delocalized ring, and the Kekul's structure is wrong. Thank you for watching. See you in my next video. Bye bye.